All right, so for the warm-up, we're just doing basic derivatives here. So just going through that power rule. All right, so we multiply to the front, take away 1. Easy peasy. All right, f prime of x, 3x squared. All right, now our 10, that's just some constant. We take the derivative, our constant disappears. So if we're looking at 3, when we take the derivative, right, we use our power rule, 3x squared, and then whatever our constant is goes away. Right, so when we go in the reverse, when I give you the derivative and I ask you to find our original, what we're going to do is we're going to go backwards. So I need to re-add 1 to my exponent and then divide away what I multiplied. And I would have this constant, right? I can see that that is true, this extra constant value that's going to go away. So you guys, obviously we're getting into introduction here, which I know you guys are no strangers to. But when we're setting these up, we're really going to be focusing on making sure we include that constant, not leaving off our constant. Okay, so then we have our general integration rules. So to start, we have our power rule, our most common. Remember, what we do is we start by adding 1 to the exponent, then dividing. So literally the exact opposite of taking a derivative. All right, then we have our constant rule that says if we're integrating something like 2x, we're able to pull the constant to the front. But be very careful, you guys. You cannot factor out a variable. All right, then we have our trig rule. So let's go ahead and fill this in. So to get cosine, the integration of cosine is sine x plus c. Sorry, funky little s going on there. Whoop, there you go. All right, when we integrate sine, we get negative cosine x plus c. Integrate secant squared, we're going to get tangent x plus c, negative cotangent x. All right, when we integrate secant tangent, we get just the secant. And finally, when it's cosecant times cotangent, we get negative cosecant x plus c. So literally the same trig rules as derivatives, just in the opposite order. All right, let's get our brains back to integration. I know after doing derivatives for so long, it takes a second to get back into the pattern. All right, so we're going to go through our process. First, we start by adding 1 to our exponent. Then we divide by that number. And finally, we add c, that mystery constant. All right, if we're given just a number when we integrate, we really are dealing with x to the 0. So when you add 1 to the power, gives us 2x to the 1, divide by 1. Or in simpler terms, you guys, when we integrate, we add on that variable, right? We add an additional variable on there. And of course, we can't forget our c. 2x plus c. All right. We just take this one piece at a time, just like when we were taking our derivatives. So this is going to give us t to the 5th divided by 5 plus 2t and plus our mystery constant. Same thing here. We're going to break up 7 into just, one piece at a time, and it's just our kind of reverse power rule here. So add 1 to the exponent, and then divide by that number. Again, we got 4y. We're going to add 1 to the exponent, so this becomes 2, and divide by that number. Finally, if we have a constant, we add on our variable y and our mystery constant. Clean this up a little bit. That gives us 2/3 y cubed plus 2y squared plus y plus c. All right, so then we're going to have these, our last two guys, look kind of scary, 8 and 9. The trick to these is rewriting them. We don't want to leave any thing in the denominator or under a radical. So we're going to use our exponent rules to rewrite these. So for instance, I can rewrite this as being integrate 3 times x to the negative 2 minus x to the negative 1/2. I can't forget my dx. All right, now I can integrate per usual. So I'm going to add 1. That takes me x negative 1. And then I'm going to divide by my negative 1. Same process over here. I'm going to add 1, but I'm going to add a fancy one. So I'm going to add 2/2. That gives me a positive 1/2. And then I'm going to divide by 1/2. Okay. This is a very ugly way to write that, right? It's kind of messy. It's a triple decker fraction. So instead of dividing by 1/2, what we can do is we can flip it and multiply. So instead of saying dividing by 1/2, I can say times 2/1, or just multiplied by 2. So when we clean this one up, we're going to get negative 3x to the negative 1. Oh, forgot my c. Minus 2x to the 1/2. Let's see. And we can even put it back into that, starting format where we have negative 3/x minus 2 times the square root of x plus c. Okay, so a similar process here with 9. First thing we're going to do, we're going to break up this fraction. So both the square root of x and the 1 are being divided by x squared. So I can rewrite it the square root of x over x squared plus 1 over x squared dx. I can also rewrite that square root as a fractional exponent. So we're going to write it x to the 1/2. Now when we simplify these fractions, what I'm saying is 1/2 minus the power from down here, minus 2. So that's negative 3/2 or negative 1.5. All right, and we are still integrating this. All we've done so far is rewrite it. Now that it's all rewritten, we can go through our regular integration steps. So we're going to add 1, but we're going to add a fancy one. So 2/2. That gives us x to the negative 1/2. And then we're going to divide by negative 1/2, or in other words, multiply by 2/1. All right, let's add 1 here. Then divide. Just gives us negative 1. And then our mystery constant c. And if we clean this up, we get negative 2x to the negative 1/2 minus x to the negative 1 plus c. Put it back in the denominator under a radical. There you go. Finally, we have our trig rule examples here. So again, we're going to take it one piece at a time. First, we're just taking the integration of 2 cosine. This 2 is a constant. Technically, we could rewrite this as such, minus, by pulling those constants to the front. d theta. Okay, kind of chunking it up so it's a little simpler. So we say the integration of cosine we know is sine. With that multiplier 2 on the outside. And the integration of sine is negative cosine plus our constant. So we get 2 sine theta plus 3 cosine theta plus c. All right, so 11's a little sneaky. We're going to need some of our pre-calc knowledge of our trig rules to solve this one. So if we rewrite this one, I could rewrite it cosine of sine x multiplied by 1 over sine x. So I'm splitting up that sine squared x. And then I can see cosine over sine. That's cotangent. And 1 over sine is cosecant. All right, so there's my rewrite step. Now that we're in this format, we can use one of our trig rules to integrate. So if we look back to our trig rules, cosecant times cotangent would give us negative cosecant x plus c. So the tricky part about this is just our manipulating with our old trig rules. This is going to be our first application example of integration. So what's the big difference here is that we are given this initial condition idea. Initial condition just means your starting point. All right, and it lets us find c. Okay, so this is going to be our first example where we're not going to have that mystery c constant at the end. We're going to start off the same, so we're going to go ahead and integrate our f prime to find our original. So our original function, we're going to add 1 and then divide. And of course, plus c. Okay, and we can clean this up a little bit too. So our original function, we could write as negative 1 over 2x squared plus c. Now we're going to use this initial condition that x equals 1, then our output is going to give us 3/2 to find this value c. So now that we found our original, we're going to plug it in. And we're plugging in both the x and the y value here. So our only variable that should be left is c. This gives us 3/2 equals negative 1/2 plus c. We got to solve for c. C gives us 3/2 plus 1/2, which is 2. So now that we found c, we have found our specific curve. Fx equals negative 1 over 2x squared plus 2. Okay, so this is our second application example. This time we're given our acceleration and we're asked to find our velocity. So we're going backwards from what we did last unit. If we have acceleration to get velocity through integration, we're going to start by finding the integration here. So we add 1 to our exponent and we divide. Constant, we just tack on that extra variable, and then we have our c. Now, we're going to be dealing with multiple constants in here, so I'm going to label this c1, just so we don't get confused on the line. And of course, I can clean that up really quick. That's 2t squared minus 3t plus c1. All right, now we're going to use the initial condition they gave us, that if our t is 1, then our velocity is going to be 6. So we're going to plug in all that information here. So v of 1 is 2 times 1 squared minus 3 times 1 plus that mystery constant. We know that's going to give us 6. We just got to clean it up and then solve for our mystery constant. So we have 2 minus 3 plus c1 is 6. And that gives us our constant is going to be 7. So our specific answer here is that our velocity is equal to 2t squared minus 3t plus 7. All right, and that's our answer to A. Now B is a very similar process. To find our original position, we're going to integrate our velocity again and then plug in our initial condition. So S of t is going to be the integration of our velocity equation from up here. So this is going to give us 2/3 t cubed minus 3/2 t squared plus 7t. And then we have our second constant I'm going to call C2. All right, because these two C's are two different variables. Then we're given a different set of initial conditions. We're set if t equals 2, then our initial position is 5. And all we have to do here is solve for that variable C2. Okay, so this is going to give us 16 divided by 3 minus 6 plus 14 equals 5. All right, let's see. That's going to end up giving us negative 25 divided by 3. So our specific answer here is S of t equals 2/3 t squared, cubed, minus 3t squared plus 7t minus 25 divided by 3. And there's our specific answer. Okay, so we have our very last example here. It's another application one. So what we're given here is that our acceleration due to gravity is negative 32 feet per second. So when we go to find the velocity, when we integrate, since this is just a constant, we're going to go ahead and tack on our variable and add that constant. I'm going to label this C1 because we're going to deal with two different constants. Now this says V0 equals initial velocity. Initial velocity would be when t equals 0. So when t equals 0, our velocity, our given velocity at time 0 would just be written VO. It's like another variable. So when we go to solve for RC, it would look like this. We'd say, okay, our initial velocity plus C1 equals VO, V0. All right, and then of course our 32 times 0 would just cancel out, and we're left with that our constant is this other variable, our initial velocity VO. So when we're writing this, we say V of t equals negative 332t plus that V sub 0 variable that we're given. All right, and this is a very similar process to finish up notes here. We're going to go ahead and integrate our velocity to get our position. Okay, so this is going to give us t squared minus 16. We have the V sub 0. This is just some constant, so when we integrate, we need to tack on a variable. And then we have our new constant of integration. Our last thing we have to do is find what that C2 means. And again, when it says initial position, that means when t equals 0. So when S of 0 is going to give us S sub 0, that kind of new variable. When we plug in 0 here, we're going to get, and once again, you're going to find that C sub 2 is S sub 0. So our final answer is right like that. All right, you guys, that's it for notes today. Go ahead and try to tackle 3-6, and I'll be checking the homework tomorrow.